Hello everyone, I'm very honored to present our inspiring research today. So our research title is gas sensor based on nonlinear copper aluminum nitride piezoelectric micromachined resonators. So my name is Zhengliang. I'm from the Loughborough University from the United Kingdom. So before I start the main content, I would like to give the structure of our presentation. So firstly, I will introduce some background about the MEMS technically and how they are used in gas sensors, and give our motivation for the project. After that, I will show the sensor structure and the methodology before I show the experiment setup and some experiment results. And at the last, I will conclude the whole research. So recently, a new technically in the microelectromechanic systems technically is proven to give high performance in sensing applications. This kind of sensors is quite small with high sensitivities, low power consumptions, and long-term stabilities. Hence, the demand for MEMS sensors is ever increasing in the last 10 years and will keep rising in the future. So among many types of the MEMS sensors, so the MEMS gas sensor receives remarkable success. So numerous sensor structures have been developed, and here are several promising examples from the literature. So the left side is microgrammetric gas sensors. So these types of sensors are normally using the coatings maybe on the top of the cantilever. So this coating could absorb the target gas and introduce mass perceptions into the system and lead to the resonance frequency shift. The right side, another proven technique could be the superconductivity gas sensing. So this kind of the gases is designed to detect the environment temperature variations due to the change of the ambient thermal conductivity. So during our research, we proposed a new MEMS gas sensing structures using the dynamic analyze a response of an aluminum nitride with piezoelectric-based weakly coupled resonators. So such a gas sensor will be a perfect solution for the environmental monitoring and other IoT applications. So, okay, so this is the main structure of my sensor. Let me get a laser pointer. Okay. So this gas sensor comprises a cantilever and a bridge resonator, represents here as the orange bars. A thin copper beam, which is a blown bar here, weakly couples both resonators. The external AC actuation will be provided on the aluminum nitride piezoelectric layers and lead to the periodic deformations, and therefore generate the vibrations of the whole systems. Here, external electrothermal voltage with thermal is provided to heat the bridge resonators and tune the resonance frequencies. So here we're using the thermal conductivity sensing. So this means that if this heated bridge contacts high thermal conductivity gases like the helium or the hydrogens, the bridge will be cooled down due to the convections, and the stiffness will be changed. So these stiffness variations would influence the resonance frequencies. So here is the first two global modes that discussed in our experiments. So you could see that the first global mode, the vibration of the first global mode is almost confined at the cantilever, and the second mode is almost confined in the bridge resonators. So we use a simple 5-mask level SLI patterning to fabricate our sensors, and you could see the cross section here. So here are our experiment setup. So the MEMS device is placed in the reaction chamber, which is equipped with a port connected to the signal generators. So at atmospheric pressure and room temperature. Two gas bottles, which contains nitrogen and the helium, so respectively provide the gas input of in the experiment. So here the nitrogen is a carrier gas, while the helium is a target gas. The mass flow controller directly connected to the gas bottles are used to control the flow values of the two gases, hence change the gas concentrations in the chamber. Laser vibrometer here is adopted to monitor the motion of the sensor, and we use MATLAB to process the raw data from the vibrometer. Here, the right figure shows the top view of the gas sensors under scanning electron microscope. So here the length of the bridge resonator is 650 millimeters, and the length of the cantilever is 300 millimeters. So this is a quite small device. So as we introduced before, so the external DC voltage is used to tune the resonant frequencies, and the 1 volt AC is applied on the aluminum nitride layers as the actuations. So here in this graph, we could find that the first global mode and the second global mode is highlighted in blue and red color lines. We could find that the first global mode here keeps same, while the second global mode experiences frequency shift with increase of the electrothermal voltage. Before the buckling point here at the 6.15 volts, the second mode resonant frequency is decreased with the thermal, while after the buckling point the resonant frequency is increased. So also we observed the two varying points at the 4.49 volts and the 6.9 volts here. So here is the frequency response. So near the varying point and the bubbling point. So the first and the second global mode are highlighted in red and blue color bars here. So from the left graph, so here it shows the frequency response near the varying point. We could find that when the electrothermal voltage increased to the 4.49 volts, so the amplitude of the second global mode is decreased, and the first global is increased. So which rivals linear energy exchange during the varying zone. Also, in this varying phenomenon, the mode shapes and other characteristics will be exchanged. Here, the right graph shows the frequency response near the buckling point. We could observe the reverse frequency shift directions before buckling point and after buckling point. So here are the experiment results for our sensors. In the experiment, we insert the increasing concentrations of the helium, which will cool down the bridge resonators, hence counteract the influence of the electrothermal heating. So here we insert the helium from the 0% to the 25%. We choose the two operation points here, one before the buckling point and one after the buckling point. The above graph shows the operations point before the buckling point and the base thermal is to 5.5 volts. And we could find that the first global mode doesn't change the resonant frequencies, while the second global mode change. And the sensing curve is highly linear with sensitivity of the 0.31% per kilohertz. The below graph shows the sensing curves after the buckling point at 6.6 volts. The sensitivity curve is also highly linear and with a higher sensitivity of the 0.9% per kilohertz. So both operation results shows that it's a very shows its great potential for the sensing applications. So now I would like to conclude our research. Firstly, we propose a new gas sensing structure using the dynamic response of an aluminum nitride piezoelectric based weakly coupled resonators. The helium sensing result shows a highly linear and sensitivity results, so which is very suitable for the IoT applications. The future work will focus on the multi-gas sensings on these structures. We prepare to introduce another sensing technique on the cantilever, and this is proven theoretically in our other research. So this is end of my presentation. If you have any questions, I would like to answer you. Thank you.